In the past year, I've been fortunate to visit a few really beautiful places, and now that I'm back home with my parents for a few months, I've been feeling inspired to recreate some of them using Unity. Most recently, I've been working on a project to recreate Mount Rainier. If you've never heard of Mount Rainier, it's the tallest volcano in the Cascades, and it's considered to be the most topographically prominent mountain in the US, as well as one of the snowiest places on Earth. It's also been designated as a decade volcano, which is basically a list of the world's 16 most potentially destructive volcanoes, and it's one of the centerpieces of the Seattle skyline. I was able to visit Mount Rainier last August, and it is by far the most beautiful place I've ever played Nintendo Switch. The first step in recreating the mountain was requiring topographic data of the Mount Rainier region. Fortunately, I was able to find a digital elevation model of Western Washington on the web fairly easily. I then used the open source application QGIS to convert the DEM files to a grayscale height map texture. To generate terrain from the height map in Unity, I create a 2D grid of vertices in the XZ plane, and then I get the Y coordinates by sampling my height map texture. Initially, when I tried using my height map, it looks pretty good from a distance. However, as you zoom in, you start to see that the game looks sort of like a cursed Minecraft clone. I believe the problem is occurring because the grayscale height map is representing each altitude with a singular byte of memory. This means there are only 2 to the 8 unique altitude values, and since altitudes in the DEM range from 600 to 4,400, the height resolution is only about 14.9 meters. One elegant solution to this problem would be to store the DEM data in an RGB texture instead. An RGB texture has 2 to the 24 unique states, so this strategy could achieve a height resolution of less than 1 centimeter. I've chosen a simpler, albeit less accurate solution for the time being. First, I sample the grayscale height map with a fairly low sample rate, and then I use a subdivision algorithm to recursively smooth out the mesh. The subdivision algorithm works by doubling the number of vertices in the mesh during each iteration. Some of the new vertices are called odd vertices, and the others are called even vertices. Odd vertices are created along each edge from the original mesh, while even vertices replace each vertex in the original mesh. The properties of both types of vertices are determined by a weighted sum of existing vertices. For odd vertices, the sum includes the 4 vertices surrounding the edge of interest. The 2 vertices on either end of the edge each receive a weight of 3/8, and the other 2 vertices receive a weight of 1/8. And for even vertices, the sum includes the original vertex and the 6 connected vertices in the original mesh. In this case, the weight of the original vertex is much larger than the other terms. Once I had the terrain mesh in place, it was time to actually shade the mountain. And if there's one defining characteristic of Mount Rainier that I wanted to get right, it's the snow. Determining where to place snow is non-trivial because if I shaded purely on altitude, I'd end up with half the mountain being snow-covered and the other half being barren rock or grass. So instead, I decided to take an approach where snow coverage depends on both altitude and slope. My reasoning being that it's unlikely for snow to stick to the face of a cliff, no matter how high up that cliff may be. The slope of a mesh can be analyzed using its normal map. Specifically, if the vertical component of a normal map is close to 1, that part of the mesh is flat, and if the vertical component is less than 0.6 or so, that part of the mesh is pretty steep. To show how the normal varies across the terrain, in this rendering I use the x, y, and z coordinates of the normal map to set the red, green, and blue values of each vertex respectively. And this means that green areas in the terrain are relatively flat, and blue or red areas are relatively steep. In practice, rather than defining a hard cutoff for the required flatness and altitude for snow to accumulate, I defined a curve to allow snow to accumulate on steeper terrain at higher altitudes, and then I created a simple shader that shades all snow vertices white and all non-snow vertices black. And I was actually quite happy with how this first attempt at snow placement turned out. It obviously looks better from a distance, and it probably doesn't actually mirror snow accumulation on Mount Rainier, but I think it looks pretty natural, and it gave me some inspiration towards an art style for the project. Once I had snow in place, I moved on to shading the rest of the terrain, and for this project, I don't think I really want to use a realistic or detailed texturing, so for the time being, each vertex color is computed by simply blending 3 colors based on altitude. I landed on using a pastel green for the base of the mountain, a brownish red for the middle, and then a purple for the top to try to give the mountain somewhat of a whimsical or fantasy vibe, but I'll probably tweak this shader a good bit in the future. You may have noticed in the recordings that the game looks a little bit different in the game view than the scene view. This is because I'm using post-processing effects that I downloaded from the Illustrated Nature pack on the Unity Asset Store. I bought the pack primarily for its stylized trees and plants, and I've been really impressed with everything so far. As you can see in the provided demo scenes, it's really easy to apply weather and seasonal effects to the vegetation, and the pack came with a pretty solid character controller that I've been using for the time being. With the Illustrated Nature assets installed, my next step was to procedurally generate vegetation. Admittedly, I'm still in the early stages of the step, but I'd like to finish the video with a brief look into what I have so far. From a little bit of research, I found a lot of people recommending Poisson disk sampling for object placement. The primary benefit of Poisson disk sampling is that you can efficiently enforce a minimum distance between two randomly placed objects, and it's relatively easy to modify the Poisson sampling method using Perlin noise to achieve a variation in object density that looks relatively natural. I won't go into the specifics of the actual algorithm, but you can find more about Poisson sampling in the tutorial I listed in the description. Within my Unity project, I created a little tool to visualize Poisson distributions with different densities and minimum distance thresholds. Here's an example of a Poisson distribution I would generate for grass placement. And here's another one I used for tree placement. And then finally, here's one I used for rock placement. Putting these distributions together, I end up with a game scene that I'm pretty happy with for now. I think I've done a pretty good job capturing some of the recognizable features of Mount Rainier without going for an art style that's too ambitious for me as someone who's relatively new to game development. If I continue forward with the Poisson sampling method, I'd probably use a similar distribution for flowers, fallen limbs, dead trees, and other objects you might find on Mount Rainier. But in my next devlog, I'll probably experiment with a few other object placement algorithms as well. Poisson sampling definitely has its advantages, but I think my tree placement as it stands looks a little bit too uniform to be natural. And in the case of grass placement, I think Poisson sampling is probably overkill, since it doesn't really matter if two grass objects overlap with one another. Anyways, I think this is a good place to end this devlog, and if you're interested in this project, I encourage you to subscribe for my next video, hopefully in a couple of weeks.